Hey guys, hope everybody's doing all right. What we're going to do today is take a look at something called the combined gas law, and we'll do some practice problems with that. The combined gas law is just when we take the gas laws from the previous lesson and we combine them, put them into one big gas law that'll solve basically any question we have relating to temperature, pressure, or volume of a gas. Let's take a quick look at what those equations were from the other day, the previous lesson, and then we'll do a couple practice problems. So three main gas laws. Here's the first one. P1V1 equals P2V2, that is Boyle's law. Boyle's law told us that pressure and volume had an inverse relationship, and this is when temperature is constant. So between your initial, which is your ones, and your final, your twos, your initial and final conditions, temperature is consistent or the same when you start and when you end for situations like this. Another one we have is V1 over T1 equals V2 over T2. That's Charles' law. And this is when pressure is constant. So pressure isn't in this equation here because we're assuming that despite what the initial and final conditions are here, the pressure is consistent for both beginning and ending conditions. And finally, we have Lusak's law, which is P1 over T1 equals P2 over T2. And this is when volume is constant. So again, volume isn't in the either condition here because we're assuming that your container is some rigid structure, like some metal or glass container that really doesn't move very much or doesn't change shape very much. All right. What we're going to do is take all of those and combine them. So combine your Boyle's law, Charles' law, and Lusak's law into one equation, and you get this. So please write this down on your note sheet so you know what it is. And it is really just P1V1 over T1 equals P2V2 over T2. If you look at it, you can find all three gas laws, within this. So you have P1V1 equals P2V2. That's Boyle's law right here at the top. P1 over T1 equals P2 over T2. That's Lusak's law. V1 over T1 equals V2 over T2. That's Charles' law. So you have all of them combined into this one jumbo formula here. All right, so what we'll do is use this to solve a bunch of gas law problems. You'll see how incredibly simple and easy this is. So practice problem number one. It says a gas initially, so half of this is just literally a reading comprehension piece. Okay, so can you read a word problem and figure out what's what? What are my initial conditions? What are my final conditions? That's what we need to focus on here. Okay, so the gas is initially at 2 atmospheres. You need to know that atmospheres is a unit of what? Well, it's a unit of pressure, right? It's not temperature, it's not volume. So you need to know that it's a unit of pressure. It's in an adjustable volume container of 10 point, that helps us with sig figs, liters in volume. So we have a pressure and a volume. It says if the outside pressure increases to 4 atmospheres, what's the new volume? So we already know what we're solving for here. There's no mention of temperature. If there's no mention of it, we could assume it's constant. It's not changing. First thing you need to do for these, you need to make a data table. Okay, so you make a little T-chart here. Okay, here's my divider line. Left-hand side is where you put all of your data. Okay, we've been through this before. I've taught students how to do problems like this since the beginning of the school year when we have word problems like this. So let's go through and figure out what's what. So we have a gas initially at 2 atmospheres. Initial volume is 10 liters. And our new pressure is 4.0 atmospheres. Here's how we would show all that. So P1 is 2 atmospheres. Make sure you have the numbers written correctly with the label there. V1 is 10 liters. P2, our new pressure, okay, it increased to 4, is 4 atmospheres. Our new volume is unknown. Our temperature is constant. I put that there so we remember. Okay, so all you have to do here is figure out what V2 is. Well, what could we do? Well, we could memorize 3 gas laws separately, or we can just use the one combined gas law. So on the right-hand side is where we put all of our equations in work. So you have your combined gas law. P1V1 over T1 equals P2V2 over T2. I can simplify this even further because you're going to say, well, what do I plug in for temperature? Well, who cares, right? There's no, it doesn't give me what the temperature is. It doesn't say what it is. So who cares? If you need to feel better, just plug in a random number for both, okay? Because it's the same on both sides, right? It's constant. So what I do is I rewrite my combined gas law without the part that's constant. So I take out my T1 and T2 because it's not involved in this equation here with this situation we have. So I end up with P1V1 equals P2V2. Now all I do is plug my numbers in. So go to your data table on the left, go over here on the right, and write everything out. you have to write things out with obviously the number and units. Okay, do not get lazy about this. That's where you make dumb unit mistakes and calculation mistakes. Just trust me on it. I see it happen all the time. So I plug in what I need to for all these. So P1 is 2 atmospheres, V1 is 10 point liters, and then P2 is 4 ATMs. Simple, easy money algebra. I solve for V2, and what we need to focus on here is how many sig figs we have in our final answer. Now, to check your work, before we even calculate this, I want to make sure we think about this. Look what happened. We have our P1 at 2 atmospheres, our P2 at 4 atmospheres. So pressure increased, right? What happened to your volume then? Volume is at 10 liters. What should happen to it? Well, if you remember, Boyle's law is the relationship between pressure and volume, right? So pressure and volume have what kind of relationship for Boyle's law? Well, they have an inverse relationship. So as one goes up, the other one goes down. So what you can do here is predict what your answer is going to be. Pressure went up. Since it's an inverse relationship, volume should go down. Your answer should be less than 10, right? Look what your pressure did. It doubled. Well, if your pressure doubled, well, your volume should be cut in half. Okay? Things are, that's how they work with gas laws and the way they're set up there. So let's see if we're actually right. Well, 2 times 10 divided by 4, there we go, gives us 5 liters. Careful, we need 2 sig figs. 2.0 has 2 sig figs. 10 and a decimal, that decimal there makes it 2 sig figs. And then 4.0 has 2 sig figs. So easy. 5.0 liters is your new volume. That takes care of it. All right, let's do number 2. Number 2, you have 6.8 liters of propane from a propane tank at a pressure of 95.0 kPa. So remember, PA is pascals. K is what metric prefix? Well, it's kilo. So it's kilopascal. It's all placed into an empty propane tank where the final pressure is 2167 millimeters of mercury. What's the volume of the new tank? All right, so we have the propane in this tank going into this tank. We want to find out what the new volume of that tank is. So let's make our data table. Our P1, 95.0 kPa. Our V1, 6.8 liters. And we keep reading, and our new pressure is 2167 mmHg. So P2 is 2167 mmHg. It says, what's the new volume? We don't know. It's our question mark. And our temperature is constant again. Okay. So we should notice something here, right? If you have your pressure 1 at 95.0 kPa and your pressure 2 is 2167 mmHg, obviously something should be like stick out to you here, right? You should be like, wait, something's not matching up, something's not right here. This is why, okay, not trying to harp on this, but this is why units are so important. This is why showing your work is so important. This is why making a data table is so important. If you don't make this data table, you just have 95 and 2167, you don't know what the units are. Easily make a dumb mistake here. But you're like, wait a minute, I have kilopascals and millimeters of mercury. Well, I have to make them the same unit, right? It's like doing a problem with meters and centimeters. Well, you can't do that. You need to make sure they're both the same unit. So what we can do is convert 95 kilopascals into millimeters of mercury or millimeters of mercury into kilopascals. And you just do that by factor labeling it. So I have that underneath here. 95 kilopascals. I want to cancel out kilopascals and go to pascals. So 1,000 pascals in 1 kilopascal. Just like there's 1,000 meters in a kilometer, right? 1,000 seconds in a kilosecond, right? You get the idea. I've had students, again, I said this before, they think PA is Pennsylvania. I'm like, okay, fine. You have 1,000 Pennsylvanias in 1 kilo Pennsylvania. Not a problem, okay? So the kilopascals cancel out. So I want to cancel out pascals now, put it on the bottom of my next step. So pascals cancels out. And I want to convert to mmHg. I use my standard air pressures right here that you never have to memorize ever, ever, ever. And then I just find my answer. I need to do the right sig figs. None of these numbers count for sig figs here. So I have 95.0 has 3, 760.0 has 4, and 101.325 has 6. So my final answer needs 3 sig figs, so I have 713 mmHg. That is this. Okay, so in your data table, you can even rewrite the new pressure as 713 millimeters of mercury. All right, moving on. We have our combined gas law. We always start with that because it just makes our life as easy as possible. Temperature is constant, so I'm going to ignore these. And I have my new equation, P1V1 equals P2V2. This is really just a Boyle's law problem. And now I plug my numbers in. So I plug in my new pressure. I have everything else here. I have my V1 and my P2. Notice when you divide both sides and you do the easy money algebra, you have 2167 mmHg over here. The mmHg cancels, the 2167 cancels. Over here, when you divide it by the 2167 mmHg. Don't judge my handwriting. The mmHg cancels. All right, so the whole idea here of the unit analysis and canceling that out. So 713 times 6.8 divided by 2167. Figure out how many sig figs this should have. Based on those 3 numbers, how many sig figs should our final answer have? All right, and that gives us 2.2. Pretend that 4 isn't there. All right, 2.2 liters as my new volume. We should have 2 sig figs. All right, 6.8 has 2, 713 has 3, 2167 has 4. All right, so I screwed that one up too when I was making my answer key here. So 2.2 liters is our new volume. That makes perfect sense because our pressure went from 713 to 2167. So the pressure increased. What should your volume do? Well, again, this is volume and pressure relationship here. It's inverse. So one goes up, the other goes down. Or if one goes down, the other goes up. Pressure went up, volume should go down. We went from 6.8 to 2.2. So it works. Okay, guys? One last practice problem, and you guys will be able to work on a few of these. So we'll start on problem number 3. Next slide. All right, guys, let's wrap this up with the last practice problem here. So it says, to what volume will a balloon initially at 1 liter and 1 atmosphere change if its temperature is decreased from 35 Celsius to 5 Celsius and pressure changed to 2.5 atm? All right, so a whole lot of stuff going on here. All right, let's try to break it apart a little bit. Obviously, first thing you need to do is make a data table, right? So especially for a problem like this, a lot of numbers here, a lot of wording going on. Just organize your work, organize your data, and then it all just falls into place. It's easy from there. So we have initially, right here, so keyword, again, that reading comprehension, initially 1 liter, 1 atmosphere. And the temperature goes from 35 to 5. So our initial temperature, 35 Celsius. So let's write all this out. So initial pressure, 1 atm, initial volume, 1 liter. That's 1.0. That's important. 1.0 has 2 sig figs in it, so keep that in mind. And then 35.0 Celsius. Everything else will be our secondary, like our second condition, right? So what it changed to. So I have a new pressure of 2.5 atm and a new temperature, and we want to find the volume. To what volume will the balloon blah 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 change? So let's get this all on paper. So we have our P2 is 2.5 atm, our V2 we don't know, and our T2 is 5 Celsius. Okay, now you have to go back to an earlier video an earlier lesson on gas laws, and we need to think of one of the problems that we had with some of our units with gas laws. One of our problems was if you had something at 0 Celsius, that implies 0 kinetic energy, but that's not true. So we had to use a different temperature scale, right? We can't use the Celsius scale because the Celsius scale doesn't represent 0 being truly 0 kinetic energy, right? We have to use the Kelvin scale instead. So Kelvin, the lowest temperature you can get to is 0, right? And that is actually absolute 0. That is no kinetic energy. So we have to use the temperature scale for all of our gas law problems. That means we have to convert into Kelvin here, right? So I do that right in my data table. So I left some space underneath to do it. You can just do it right next to it. All you have to do is take your Celsius temperature and add 273. right? This is a mistake students forget to, they forget to do this all the time, and it's so easy. It's just slow down a little bit, try to think about some of the details here. And one of those is what temperature scale you use. So T1 is 35.0 plus 273, gives us 308 Kelvin, and T2, instead of 5 Celsius, it is 278 Kelvin. Okay? So now, let's check everything else out. P1 is in ATM, P2 is in ATM, well, that's great, and V1's in liters, and V2, if we solve it, should be in liters. So what we'll do is start out with our combined gas law like we always do. Nothing's consistent here, right? Pressure, volume, temperature, all changing. So like on the previous examples, we took out one of the terms that we're not using. Here we need to keep all of them there. So let's keep them there, not a big deal. And I want to show you how to rearrange this, okay? I've said this all year. Anytime we do a math problem with a fraction in it, fractions make people uncomfortable, right? Fractions even make me uncomfortable. So the first thing I do is get rid of the fraction here, okay? So I want to reorganize this so I have everything all in a line, right? So the easiest thing to do is to cross multiply. So cross multiply, like you learned in math class 100 years ago, and rewrite what you have. This is where it gets a little confusing because you have a lot of 1s and 2s here and a mess. So reorganize. P1 V1 T2 equals P2 V2 T1. Okay? Now, what don't we know here? We don't know what V2 is. That's our unknown, right? So solve for V2. So to solve for V2, we divide both sides by P2 and T1. So I'm going to do that, okay? If I divide both sides by P2 T1, see, I'm screwing up, you're going to get, it'll cancel out over here. And you'll get P1 V1 T2 over T1 P2 equals V2, right? Easy. So you can see where a dumb mistake could occur here. It happens all the time. You screw up one of these subscripts, the 1 or 2, and then it's a mess, right? So slow down a little bit, show your work, and minimize the chance of a mistake like that occurring. Okay, plug it all in. Make sure I did it right here. P1 is 1 atmosphere, V1 is 1 liter, T2 is 278 Kelvin, right? It's T2, right? Students always go P1, V1, T1, and then put the 2's on the bottom. Well, no, it's not what the equation looks like. And then your T1 is 308 Kelvin, and P2 is 2.5 ATM. Kelvins cancel right there. Atmospheres cancel right there. Okay, I'm not going to mess this one up this time. How many sig figs do we need in this answer? We need 2, right? 1.0 atmospheres has 2 sig figs. 1.0 liters has 2 sig figs. 278 Kelvin has 3. 308 Kelvin has 3. 2.5 has 2. So we round to 2 sig figs here. And if you do that correctly, I think you get 0.36 liters of gas. Okay, that will be your volume. That will be your V2 here for this problem. So it's just a matter of making your data table. Always use the combined gas law. Just the easiest thing to do. If you have a term that's not in your data table, like on the previous example, there were no temperatures, we'll just get rid of it. You'll do some where there might not be any pressures, we'll get rid of it. If there's no volumes, get rid of it. But if there is, obviously keep it in there. Reorganize, do some easy money algebra, and we should be in good shape. All right? So what you guys will do is either tonight or the next day in class, you will work on some select problems. So check the lesson plan roadmap or Edpuzzle, and it'll tell you what problems to work on, so you're not doing extra. All right? So certain problems you'll work on, do some practice with this, answer key will be posted, and you should catch on with this pretty quickly and pretty easily. All right? Thanks, guys.